Hello, welcome to all. In the previous lecture, we completed the magnetostatics. Okay, in the previous lecture, we studied about the ballistic galvanometer and its damping and damping correction. Okay, with that, magnetostatics is completed. Now, we are going to study in the next unit electromagnetic induction. Electromagnetic induction. Yeah, let us start this electromagnetic induction. Yeah, we know that uh, any current carrying conductor will induce some magnetic field around that conductor. Okay, this was discovered by the Oersted. Yeah, we know that. Okay, this is one phenomena. Just Oersted placed one magnetic needle in the very immediate surroundings of the current carrying conductor. Then what happened? He noted the deflection of that magnetic needle. Okay, the deflection of the magnetic needle is only possible when there is some perceptible magnetic field where it is placed. Actually, there is only current carrying conductor, no particular magnetic field. So, what we can understand here is that current carrying conductor itself producing, or the current within that current carrying conductor is producing the magnetic field. That's why we call that magnetic field as an induced magnetic field. Okay, this was discovered by the Oersted. Right. Okay. Yeah. Yeah. We know uh, this much information. Okay, with this, let us go for this new topic. Outline of today's lecture is Faraday's laws of induction, integral form of Faraday's law, differential form of Faraday's law, and Lenz's law. Okay, let us go one by one. Now we know that uh, a current carrying conductor or current inside that current carrying conductor is able to produce the magnetic field. Here, the current or the charge in motion is creating the magnetic field. Okay, this we know already. Now we are going for another major discovery which is of very fundamental importance. This discovery was made by the Michael Faraday, the great scientist who discovered so many things in his lifetime. Okay, Michael Faraday discovered in the year 1831 a new phenomena called electromagnetic induction. Okay, this is our topic of discussion. We are particularly studying this unit itself, electromagnetic induction. This phenomena was discovered by the Michael Faraday in the year 1831. Okay, what is this electromagnetic induction? Yeah, it is a generation of induced current by a changing magnetic field. That means creation of current by the magnetic field. In the Oersted experiment, what we observed, current itself is creating the magnetic field. Here, in Faraday's experiment, changing magnetic field itself creating the current. That means it is producing some induced current or it is producing some induced EMF. Okay, This was discovered by the Michael Faraday in the year 1831. Okay. Here we have to note the difference between Oersted's discovery and Faraday's discovery. Okay, both these discoveries are very fundamental in the history of the physics. Okay, yeah, we have to understand these two discoveries, and we have to um, separate the one from the other. Both are different. They discover different phenomena. Okay, in one phenomena, the magnetic field is induced by the current flowing inside the conductor or the moving charge. That is Oersted's discovery. What Michael Faraday discovered, whenever there is a varying magnetic field, then it can able to produce a current in a conductor placed in that field, okay, or in a coil placed in that field. Okay, in Faraday's discovery, the magnetic field is creating the current. In Oersted's discovery, current is creating the magnetic field. Okay, we have to note this difference before going to study the Faraday's law or Faraday's laws of induction. Yeah, this phenomena is called, that means production of induced EMF by a changing magnetic field is known as the electromagnetic induction. This phenomena itself is known as the electromagnetic induction. Okay, the law governing this phenomena is known as a Faraday's law. Okay, Faraday's law of induction. Yeah, one thing we have to note: the Oersted's experiments. You are taking a current carrying conductor in which the charge is moving. Charge is moving. Whenever the charge is in motion, then each and every charge will be suffered by a magnetic force. That's why you have force, magnetic force acting on a conductor placed in an external magnetic field. Here also, see, whenever there is a no motion of the charge, there you do not have any induced magnetic field. That's why you do not have any magnetic force, okay, acting on it. The similar thing happens in Faraday's discovery as well. Faraday's discovery is always linked with the changing magnetic field or the magnetic flux. This is important. See, in Einstein's discovery, whenever there is no motion of the charge, then you have no magnetic field there also. Okay, so here, whenever there is no change in the magnetic field, then that type of magnetic field is unable to create the current. That means is unable to induce the current in the conducting loop placed in that magnetic field. Okay, this we have to note. Yeah, here variation of the magnetic field is must to produce the induced current or induced EMF. Whenever there is no variation of the magnetic field, there is no induced current at all. There is no induced current at all. So in this way, you have to compare both Oersted's law and uh, Faraday's law. Okay, here the factors are changing. Cause is changing into effect, effect is changing into cause. Whenever you come from Oersted's discovery to Faraday's discovery, but the thing is same. There are some similarities. Unless your charge is moving there, in Oersted experiment, there is no magnetic field. Here also, unless your magnetic field is changing, you have no induced EMF in the coil placed in that magnetic field. This you have to know. These are the similarities you have to observe. Okay. Yeah. Now, what is changing magnetic field? See how many sources of magnets are there. If you take a permanent bar magnet, if you take a permanent bar magnet, okay, see north pole, south pole. This is a permanent bar magnet. This is able to create a stationary magnetic field. It is able to create, suppose that you are placing this magnet on the table, it is able to create some permanent magnetic field. How the field lines are running here, from which pole to which pole? Field lines are running from north pole and terminating in the south pole. Okay, they are starting at the north pole and terminating at the south pole. Okay, so that's why you see here the magnetic field around this bar magnet. This is stationary magnetic field. This is stationary magnetic field. When do you have the changing magnetic field? Changing magnetic field. That means in one particular place, the density of the field lines should not be the constant. Whenever it is constant, the field is stationary. Suppose that you are selecting this area. Here you have two magnetic field lines. Okay? At any time, why? Because it is a stationary magnetic field, always you are finding two magnetic field lines. Okay, in this area. If it is a changing magnetic field, then what happens? This number of field lines passing through this area may change from time to time. Why? Because that is the changing magnetic field, variable magnetic field. So how can you increase or decrease the number of field lines passing through this area? Here you have to displace this magnet. You have to displace. You have to move this magnet. Then what happens? If you move just like this, only one field line passes through this area. That means in this particular area under consideration, you are creating a variable magnetic field. So how to create the variable magnetic field? Just by displacing the permanent bar magnet. Permanent bar magnet. Okay, this is one way. This is one way. Now you see your magnet is now moving. Okay, you are moving your magnet like this. Then what happens? In this particular area, you will get the varying magnetic field. Okay, this is one way of doing this. One way of doing this. Otherwise, you just take, okay, here with reference to some particular point, okay, this magnet is moving. This magnet is moving. Okay. Now, another way of getting the varying magnetic field is here your area under consideration is stationary. You are moving the magnet. Okay. Next time you may just keep the magnet as it is. Next you may change. You may move this area under consideration or the reference point. This area. Okay. Then what happens? You just take a cardboard which is in the shape of square or rectangle and just move that cardboard in the area around this magnetic field. At one time it may intersect two field lines, at the other time it may intersect only one field line. Then in your area under consideration, that means on that cardboard, on that area under consideration, the magnetic field is still changing. Still changing. Okay. So in this way, here magnet is moving. Magnet is moving. In the second case, you may change the reference point. Okay. Here, what is moving? Reference area is moving. Reference area or point is moving. Okay. So, in order to get a changing magnetic field at a place, what you have to do? Either you have to move the magnet or you have to move your reference area. Okay. If you change both this magnet and this area, then also you can achieve the variable magnetic field. But movement in any one of these two things is mandatory in order to get the variable magnetic field. Okay, what is the other way of getting the variable magnetic field, time varying magnetic field? Okay, you may select electromagnet. Okay, you have to select some electromagnet. Okay, I will write here. Next, you may consider an electromagnet. Okay, instead of taking a permanent magnet, you are taking some electromagnet. Okay, some electromagnet. Okay, current is passing like this and coming out like this. Here you have the magnetic field. See, current is flowing through this coil. This coil is behaving like the electromagnet. In order to change the strength of the magnetic field, what you have to do? You have to change the current. By changing the magnitude of current with time, you can achieve the varying magnetic field. Okay? Then, this type of magnetic field is also able to produce the induced current inside this closed loop, conducting loop. So, in this three ways, you may achieve the varying magnetic field. Here, in this third case, um, you need not to change the position of either the magnet or the loop or the reference area. Okay. In this area, you want to see the magnetic field in this area. Magnet is here. As you change the magnitude of the current, then what happens? The magnetic field in this area also changes. In this area also changes. Okay. Right. In this area, we are placing our loop conducting a loop in order to get the induced current. It is different thing. Just we are talking about only varying magnetic field without referring to the coil. Okay. Yeah. In the previous two cases, how to achieve the varying magnetic field? Either you have to move the reference area or you have to move the magnet. So you have to maintain the relative motion between the reference area and the coil. Okay, in a single sentence, how can you state those two cases? You have to maintain the relative motion between your reference area, reference point, and the magnet. Okay, and the magnet. In that reference area, actually, we place a conducting loop in Faraday's experiment. Okay, yeah. In all these three cases, you have some induced current. You have some induced current. Okay, yeah. This varying magnetic field, what is the meaning of a varying magnetic field? The number of field lines passing through particular point is changing. That means magnetic flux at a particular point is changing in the varying magnetic field. And that you have to note. That has to happen in order to observe the induced EMF or the induced current. Okay. Yeah, that is a precondition. See here, you see the slide. Now, there is a coil. Okay. There is a magnet. Permanent pole is there. Coil is there. An ammeter is connected to that coil. Okay. In the first case, the first diagram, both the coil and N, that means that magnet, are stationary. That means immediately next to that pole, you have static magnetic field. In that case, you have no induced EMF in the coil, no induced current in the coil. See, you take the second case. In the second case, you are pushing the magnet into the coil. That means magnet is in motion. That's why you are having varying magnetic field. Now it can able to produce the induced current in the coil. That means that is noted in the ammeter connected to that coil. Or you may connect galvanometer as well. Okay, yeah. So in the second case, you have varying magnetic field. Okay, where in the area, in the reference area where the coil is placed, where the coil is placed. Next, you go for the third case. There, the magnet is stationary in this case, but the coil is moving towards the magnet. Okay, that means here you are placing coil in the reference area. You are moving your reference area. Okay, within the surroundings of that magnet. That also cause a variation in the magnetic field in that particular area where the loop is placed. So in the third case, case C, also you have varying magnetic field. So in this case also, your ammeter gives you the non-zero deflection. That means you have induced EMF inducing EMF. Why? Because in the latter two cases, varying magnetic field is achieved. Varying magnetic field is achieved. Okay, that you have to. That means when the variable magnetic field condition is achieved, there must be a relative motion between both the magnet and the coil. So in order to get the induced EMF, there must be, okay, a relative motion between the magnet and the coil. Magnet and the coil. This is maintained in case B and case C. Figure B and figure C, relative motion is there. Okay? Either you may move both of them, but you have to move at least one of them in order to get the variable magnetic field. That means in order to get the induced EMF. Okay? Right. Yeah, you can see here. Yeah, one coil is there, closed circuit is there, okay, loop is there, yeah, in which the coil is placed. An ammeter is placed in that loop. The circuit is closed. Now you are bringing the north pole of a permanent magnet, okay, near to the coil, near to the coil. Earlier, you have no current in the circuit loop. That means your meter earlier was showing zero reading. Now your meter is moving away from the zero. What is the reason for that? Ammeter only responds to the current. There is a magnet. Due to the magnet, we are having current reading. What is the meaning of that? That magnet is creating the current inside that coil or that loop. That's why we are having the deflection of the ammeter. Why? Because ammeter responds to current only. There must be uh, a current. That current is induced. What we assume here, that current is induced. Some current is generated here due to the motion of that magnet. Okay, we call that current as an induced current or induced EMF. Okay, right. Now let us go for the exact definition of the Faraday's law of induction. So far, we discussed about the electromagnetic induction, okay, uh, phenomena, okay, and the conditions needed for the electromagnetic induction, okay. Now, let us state the exact result of the Faraday's experiment or the Faraday's law. or the Faraday's laws. Yeah, we are studying this Faraday's discovery as Faraday's laws of induction. Okay, first one law as just a qualitative statement. The next law we are stating as the second one as the equation. Okay, quantitative. It gives you the quantitative definition of the EMF. First one just tells you the origin of the induced EMF. Second law will give you the okay. Not it is not necessary always to take the one as a law, first one, first law and second law. Okay, you may also just state this as a single definition, but we are giving this as a Faraday's laws. Yeah. First thing, let us take first one as yeah. It will just give you the origin of EMF. Okay, induced current. Okay, you just see that law. You just go through that law on the slide. An induced current is produced in a closed conducting loop upon a change in the magnetic flux enclosed by that loop. Okay, this is one Faraday's law. That means there is a change in the magnetic field. It hints you the presence of variable magnetic field, changing magnetic field. Okay, yeah. A conducting loop is there. Okay, here you have okay, a conducting loop. Here you have a conducting loop, right? Now, here you are having some magnetic field. You are having some magnetic field. Okay, see these are the field lines. Okay, suppose that you are placing your coil like this, field lines are coming out like this. Okay, yeah, yeah. How many field lines are enclosed by this conducting loop? This is a conducting loop. Okay, it is made up of a conductor. See how it is enclosing some field lines, magnetic field lines. Why? Because we are placing this in a magnetic field. Whenever whenever the flux enclosed by this loop changes, then what happens? An induced current, an induced current will be produced in this coil. Will be produced in this coil. Okay. Whenever there is a, if you are changing the field lines from 3 to 2, then what happens immediately? Some current is induced in this loop. Some current will be induced in this loop. Okay. Whenever there is a change in this magnetic flux, then what happens? Actually, it is changing from number of flux changing from 3 to 1. See, number of we are changing the number of field lines from 3 to 1. Then what happens? There is a change in the flux. Okay, enclosed by this conducting loop. Then immediately you observe some induced EMF, induced current inside of this coil. If you just place an ammeter here, then you have non-zero value for the current in this ammeter. Okay. Yeah, this is what about the first statement of the Faraday's law. Second one, we are defining this in two parts. Okay. First one is giving just qualitative nature of the induced EMF. When when do you have the induced EMF? When do you have the induced EMF? Whenever there is a change in the number of field lines enclosed by that conducting loop, okay, then you have the induced EMF or the induced current inside of that conducting loop. Okay, Next, second one gives you the details of this induced EMF, second law. Okay, second part of this law. Yeah, what is that law? Magnitude of induced EMF. You see the slide? The magnitude of induced EMF is directly proportional to the negative rate of change of the magnetic flux enclosed by that loop. Okay, if you try to write a mathematical form of this, then you get EMF is equal to minus of d phi or d phi b, whatever you like, dt or dou phi by dou t. What is the phi here? Where phi is the magnetic flux. Okay, where this change is occurring within that closed conducting loop, within that closed conducting loop. Earlier we considered the case of uh, changing of phi from three field lines to one field line. So there is a change, there is a unit change in the flux. By taking that change, d phi, then you may calculate the induced EMF in how much time that change is occurring in d phi. Then this ratio itself gives you the EMF with negative sign, with negative sign. Okay, negative rate of change. What is this? What is this RHS? Negative rate of change of flux. Negative rate of change of flux. So, what the second part of Faraday's law is saying? The negative rate of change of flux linked with this with that conducting loop is giving the induced EMF in that loop, giving the magnitude of the induced EMF in that loop. So what is the second part of this Faraday's law? The magnitude of induced EMF is directly proportional to the negative rate of change of flux enclosed by that conducting loop. Okay, this is the second part of the Faraday's law. It will give you directly a mathematical form for the EMF. Mathematical form for the EMF. Okay, this is what the Faraday's law of induction or Faraday's laws of induction. Okay, you must take this as a single law as well. Right. Now we have EMF is equal to minus d phi by dt. Now after this we are going to discuss about the integral and differential forms of Faraday's laws of induction. What is the differential form and what is the integral form of this Faraday's law of magnetic induction? Faraday's law of induction. Okay. First, let us. Okay, by default, we are not getting the integral form. Okay, like in the previous cases. Okay. Here we have to transform it to integral form, and after that we have to transform it into the differential form. Okay, first let us discuss about the integral form of this Faraday's law. Yeah, before that we are taking a coil. Okay, if it is of only one turn like this, then the EMF induced in this coil will be given by EMF is equal to minus d phi by dt. Suppose that you have n turns, n such loops in your coil. Suppose that you are having n loops in your coil. Then what will be the induced EMF? EMF is equal to minus of, then your flux becomes n times. Okay, so d n phi by dt. Okay, this is equal to minus m d phi by dt. So EMF is equal to minus n. Otherwise, I will write here EMF is equal to minus n d phi by dt. Okay, this is Faraday's law for a coil having n turns, and in that case, your basic Faraday's law transforms to this equation. Okay, so in that case, you have to write n multiplied by d phi by dt. Okay, only one change is you have to multiply this d phi by dt, rate of flux, with n, number of turns in that coil. Okay, sometimes this equation is also called as Newman's law. Okay, yeah. Now let us try to find the integral and differential forms of Faraday's law. So Faraday's law of induction. Okay, first let us derive the integral form. Integral form of Faraday's law. Okay, integral form of the Faraday's law. Okay, right. You can see this on the slide as well. Yeah. First of all, take the Faraday's law, basic Faraday's law from the Faraday's law. Just now we studied about this equation d phi by dt. Okay, right. What is this? It is related to electricity or magnetism. This is related to magnetism. This is related to electricity, electromotive force. Okay, because you know the electrostatics, you know the relation between the potential and field. Here, you may write this as you may write this as EMF is equal to, what is EMF? It is a potential. You can write this as integral E dot dl. This is the induced EMF. Okay, within the coil. Within the coil. Okay. Now let us take the definition of flux as well. Okay. Here, this is by using the definition of field and potential. Simply, potential is equal to field into distance. Okay. dl. Okay. Now, let us take the definition of flux by using the definition of flux. This is related to magnetism. Phi is equal to integral B dot ds. We know this definition. Why? Because we studied this in electrostatics, we studied this in the magnetostatics. Okay, otherwise I will write here. By using the definition of magnetic flux, I will write here. By using the definition of magnetic flux, phi is equal to integral B dot ds. Okay, now you take these two things. EMF, now you are having EMF is equal to this much and magnetic flux is equal to this much. You substitute these two things into this equation. Say this is equation number 1, say this is 2, say this is 3. So from equations 1, 2 and 3 we have, okay, what happens here? By EMF you replace this thing, integral from equation number 2 E dot dl. Okay, now for the flux from the equation number 3 you replace this thing. Okay, integral B dot ds. Now this becomes equation number 4. This is the integral form. Why? Because on both sides we are having integrals. Okay, of course we are having change in the integral. Right. This is okay. It does not assumes any importance like differential form. Okay, it is not the standard form. This is called the integral form of Faraday's law. Okay. Yeah, give some number as before 4. Okay. Right. What is integral form? The transformed basic Faraday's law. Integral E dot dl is equal to minus of d by dt of b dot ds. B dot ds. Now let us go for the differential form. Next, differential form of differential form of this is very important. It is a standard formula used everywhere in theoretical physics. This form is very popular. Okay, for that we have to start from the integral form. Okay, we are having this equation in our hands. Yeah, the integral, I start from the integral form. The integral form of Faraday's law is okay this much. Okay, now we are deriving the differential form of the Faraday's law of induction. Now you may write this side minus d by dt is here. Huh? You just keep only minus outside and take this d by dt into inside of this integral. Take this inside of this integral symbol db by dt dot ds. That means we are taking this differential symbol into within the integral. Okay, we are writing this d by dt inside of this integral. Then we are having dou b by dt dot ds. Okay. Now on this side, on the LHS side, you have the same thing. Okay, r integral e dot dl is equal to this much. Okay, now let us concentrate on this LHS part. Using the Stokes law, now let us try to use the Stokes theorem of vector analysis. Okay, using the Stokes theorem, using the Stokes theorem of vector analysis, you may write this LHS as surface integral curl E dot ds. Why? Because Stokes theorem converts linear integral into surface integral. Okay. Yeah. Therefore, now you have here curl E dot ds. Okay. Therefore, integral curl E dot ds is equal to, okay, on the RHS side we are already having dou b by or db by dt dot ds. So on both sides you now have surface integral only. Surface integral only. So now you may write this as curl E is equal to minus dou b by dB by dt, or I'm writing just dou b by dou d, dou b by dou t. Okay, now you can see this on the slide as well. Right, now you have curl E is equal minus of dou b by dou t. What is the definition of curl E? Otherwise, you may write this as del cross E is equal to minus of dou b by dou t. According to this differential form of Faraday's law, here you see on the slide as well, the time variation dou by dou t of B means the time variation of magnetic field at a point is equal to the curl of the electric. Okay, the time variation of the magnetic field at a point at a point in the field is equal to the curl of the electric field vector at the same point. Okay, this is what the physical statement of a differential form of a Faraday's law. What is this? This is called differential form of. This is called differential form of Faraday's law. Okay, this is called differential form of Faraday's law. Okay, del cross E is equal to minus dou B by dou t. Yeah, in fact, this is one of the Maxwell's equations. Okay, what is this? Actually, this is the differential form of the Faraday's law. See, in the differential form, um, the law is in very compact form. Okay, this Faraday's law looks very simple and very beautiful. On one side you have magnetic field, on the other side you have electric field. This shows you the equivalence between magnetic field and electric field. That means here the change in the magnetic field is creating the electric field, creating the electric field, or creating some induced EMF, or creating some current. Okay, right. This is what the differential form of Faraday's law. Okay, differential form is a very standard form. It is very important in theoretical physics. Okay, let us stop with this. Thank you.